My first bonus presentation is going to be over a concept known as the Binomial Theorem. And this is something that's actually used in areas in addition to probability. In fact, you use them to expand polynomials, something I'll also show you at the end of this video. But it's something that can be used in probability problems that might be a little bit lengthy if you didn't have this approach to use. So here's the basic idea. The basic concept is pretty simple. We've done a lot of probability problems where you're asked for the probability that the same event occurs 3 times in a row, or the same thing happens 4 times in a row. Or maybe we ask for the probability that it never happens. Or maybe we ask for the probability that it happens every time but one, and you can find the probability that it never happens and subtract that from 1, and that means it happens all the rest of the times. There are different things that you can do that allow you to figure out some of these situations. What we've avoided is situations where you have maybe 5 or 6 repetitions and then saying, what's the probability that you're successful, maybe 3 or 4 times out of that. We've done it occasionally when we've been doing dice rolling problems, but we haven't really, and in those cases you can just list out all the possibilities. But when the number of possibilities gets more difficult, or the percentages are not 50-50 or something like that, these problems get a little bit more complicated. So that's what the binomial theorem is going to allow me to handle, those types of situations where we have some specific thing that isn't just everything happening or everything not happening. So let me give you a more clear example. The example I'm going to look at in this video is an example in which I have a coin that's not a fair coin. Maybe it's bent, maybe it's weighted strangely, but for some reason this coin has a 40% chance of landing heads, and it has a 60% chance of landing tails. And I'm going to calculate the probability that if I flip this coin 5 times, that 2 of those flips will be heads. Now, if you think about that a little bit, that's something that I could calculate using other methods. For example, I could list out all the different ways that I could get exactly 2 heads, and I could find each of those probabilities. For example, I could have heads, heads, then tails, tails, and tails. Or I could add the probability. I could have heads, tails, heads, tails, tails. Or, and I could find the probability of heads, heads, tails, heads, tails, tails, heads, tails. Or, and I could just keep listing all those probabilities out, and eventually I could figure out my total. But in a lot of cases that can be pretty challenging. So we're going to do this a little bit differently, although even thinking about this, you may have already come up with a shortcut that you might be able to use. So here's the idea. The basic idea is relatively straightforward. What I'm going to do is forget about all of these different arrangements for right now. I'm going to find the probability just of one ordering of flipping a coin 5 times and having 2 heads and 3 tails. Okay? So I'm just going to find the probability of flipping 2 heads followed by 3 tails. I'm just going to ignore the other possibilities for the moment. Okay? So there are actually 5 different events that have to happen here. There's a 40% chance of flipping heads on the first flip. There's a 40% chance, and by the way, to try to break this into pieces, what's really happening here is I'm looking for the probability of heads and tails and tails and tails. These are independent events. I can multiply these probabilities if you wonder what I'm doing here. Now, the probability of flipping tails on the coin would be the complement of flipping heads. So I can take 1 minus the 0.4, and that leaves me with a 0.6 probability, and a 0.6 probability of tails again, and a 0.6 at the end. And so what I end up here with in simplified form would be 0.4 squared times 0.6 squared. Okay, that's the probability of just having this. Okay? Now if you think about it a little bit, the probability of getting any of these other things would still have the same numbers. This would be 0.4 times 0.6 times 0.4 times 0.6 times 0.6. It's going to work out to be, there should be cubed there. It's going to be, each of those is going to work out to be the same thing as the first. So really all I need to do here is to figure out how many different orderings of these heads and tails can I have. Well, if you think about what's really happening here, really what I have is I have 5 things, 2 of which I want to be heads. And, you know, choosing this as heads and this as heads is exactly the same as choosing heads here and heads there. So as far as the orderings go, although it kind of looks like it's ordered, it's not really ordered in the normal sense we would think as far as like a first, second, third place in a race. So I'm going to do this very simply. The number of different ways that I can have 2 of those 5 flips being heads, that's just picking 2 heads out of a group of 5 flips. That's really just the combination of 5 taken 2 at a time. Okay, and if you want to work that out, that's 5 factorial over 3 factorial, 2 factorial. That's just 10. Okay, so what I end up getting here is the combination of however many repetitions I have, the number of times that I take is the number of successes I want, times the probability of the successes taken to the power of how many you want, times the probability of the failures taken to the power of the number of times that you want that. And if you did multiply this whole thing out, this ends up being, in the end, actually ends up being 10 times 0.4 squared times 0.6 cubed, and it ends up being, let's see, 10 times 0.4 squared times 0.6 cubed. Okay, that is 0.3456. Okay, so it turns out that a little bit more than a third of the time, if I had this coin that only came up heads 40% of the time, about a third of the time I would have exactly 2 heads on 5 flips. And clearly you could use this to find the probability of having 3 heads, 4 heads. Of course, 5 heads would be easier to do using other methods. No heads would be easier to do using other methods. But a lot of times those middle values, 2, 3, 4, those kinds of things are easier to do using this kind of approach. Now there is a formula for this. And the formula for this may look kind of complicated. You may understand what I've just chosen here, or what I've just shown you here, but I do want you to be aware of what the formula looks like. This is actually referred to as a binomial probability distribution, or a binomial function. And the formula for this, for the function, ends up being p of x equals, and x in this case is going to be it's the probability of the number of times that you want your event to be successful. So in this case I found p of 2. And it's equal to n taken x at a time times a raised to the x power times b raised to the n minus x power. And if you look at this and you say, whoa, what are all these numbers here? Pretty simple. N is the number of repetitions. X is the number of successes that you want to have. A is the decimal probability of a success. And B really is just a complement of that. It's actually 1 minus A. That's just the probability of a failure. So for the example problem I had over here, N, of course, would end up being the number 5 because I had 5 repetitions. X would end up being 2 because I want to have 2 successes. Probability of success was 0.4, probability of failure was 0.6, And you can see those numbers filled into the formula there. So very convenient, something that can be used in a lot of different situations when things start to get a little bit complicated to try to use more basic methods. In the second part of this video series, I'm going to explain a little bit about how the binomial theorem also applies to polynomials, and that's something that you'll see used in a lot of Algebra 2 and pre-calc classes.